Hey there, welcome back to another Ask Our Experts. I'm Ulysses, your host for this series, and we continue answering questions about clocks and timing. And in this episode, Sieg provides a definition of phase as it pertains to timing applications and provides some examples. Sieg, what is clock phase?
Okay, Ulysses, it sounds like you're asking me to provide you a definition of phase. So there are many definitions of phase that we could use, but I'm going to use this definition for our purposes. Phase is the location on the time axis where an event occurs relative to a specified measuring point. Let me say that again. Phase is the location on the time axis where an event occurs relative to a specified measuring point. Let's take, for example, an old-fashioned clock that goes tick, 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 one time each second. Now, we of course can represent these ticks as a clock rising edge along the time axis, the x-axis. Ideally, these ticks would occur at 1.00 second rising edge, 2.00 second clock rising edge, 3.00 second rising edge, and so forth. But let's say that this clock, during its first period, the tick occurs at 1.01 seconds. This rising edge's location is now 0.01 seconds off from its specified measuring point. We can call this difference in location the phase. Or during the next period, let's say the clock rising edge occurs at 2.02 seconds. The phase difference versus that specified measuring point is 0.02 seconds. And, for example, during the next period, the clock rising edge may occur at 2.99 seconds. In this case, the phase is a negative 0.1 seconds. Up to this point, I've been expressing phase in terms of seconds, but there are many units we can use to express phase. So, for example, we can express phase in terms of a period. A period is also often called a UI, a unit interval. So, for example, 0.02 seconds of phase is the same as saying 0.02 UI. Or perhaps you're familiar with expressing phase in terms of degrees, where there are 360 degrees per period. And this is a 1 Hertz clock, so 1 period is 1 second. So therefore, 0.02 seconds equates to 360 degrees per second times 0.02 seconds. That equals 7.2 degrees. Now, as engineers, we are typically comfortable referring to phase in radians, where there are 2 pi radians per second, or per period. This is a 1 Hertz clock, so a period is 1 second. If we choose to express our 0.02 seconds of phase this way, it is 0.02 times 2 pi radians per second, which gives us 0.04 pi radians per second. Now, phase and frequency are related to each other. Let's say, for example, that original clock we were talking about started going faster and faster, having a higher frequency. It went tick, 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 like that. Well, while the frequency is increasing, the phase is also increasing, and we need a way to describe that. That, my friends, is what we are going to discuss in the next video.
Thank you, Sieg, for the insight of how clocks can fall into errors and what the acceptable range of phase can be in a clock. For more information about clock phase, make sure to check out the link in the description below. And as always, don't forget to subscribe to our YouTube channel to be the first to know when we have more insights from our experts. Bye.